The system timer is linked to the start, stop and reset switches, so it's very easy to time your program, assuming it runs for more than a few seconds. Now, the more advanced emulations can control it from within the program and have access to higher resolution times, but for now I'll just use it in basic mode. So how about measuring the speed of one instruction? Well, toy B has a useful instruction called decrement and jump if not 0, so it should be very easy to measure that. Now, later I'll look at some toy A programs which use the keypad, and these are based on the Princeton University computer course, and I'll modify them to measure their performance. So first up, a very simple toy B loop. Now, I may have shown this earlier, but it won't hurt to do it again on the latest version of the machine, as there have been quite a few changes, so performance may have suffered a bit. I'll just load toy B. Right, now for the loop. It's a 7000 instruction, which says decrement register 0 and jump to address 0 if the register is not 0. And the final instruction is a halt, which is all noughts. So there we go, address 0, 7000, address 1, 0. Okay, I'll just single step this so you can see what happens. Reset and step. Now, because I've done a reset, register 0 started out as 0, but the first decrement has caused a wrap round to all Fs, which is just over 65,000. Now, this is obviously not 0, so the jump will take place and the program counter will stay at 0. I step again, program counter stays at 0. And you can see register 0 is counting down. Now, eventually that will be 0 and the program will no longer jump, so it drops through to the halt instruction and the timer will stop. Okay, I'll just run it at medium speed. And the counter is counting down. Okay, now for full speed. Right, and it's taking about a second, although the resolution on this counter is only down to 1 second anyway, so that's not very useful. Okay, let's surround this loop with another loop and increase the runtime. I'll use another register, register 1, for the secondary loop. So the new program is a 7000 as before, but the next instruction, instead of being a halt, we'll put in a 7100, which says decrement register 1, and if it's not 0, jump to address 0. So then we'll carry on decrementing register 0. If you got that right, I think. Next instruction is a halt. Okay, reset and run. And register 0 is counting down as before, but this time register 1 is counting down at a slower rate. But it's going to take a very long time before this gets to 0, so I think you overcooked it. So I'll make the outer loop smaller by preloading register 1 with a start value. Now, I did some tests earlier and 8 was a reasonable compromise. So I'll start a new program, and this time, if I'm preloading register 1, I might as well preload register 0 just to make the program more robust. So we want a B00 0, which says load register 0 with 0. We want a B108, which loads register 1 with the value 8. Now for the decrement and jump, we want 7002, which says decrement register 0 and jump back to address 2, which is where it is if it's not 0, and then a 7102, which decrements register 1 and also jumps back to address 2. And then we want a halt. I'll just check that. B000, B108, 7002, 7102. Halt. Okay, reset and run. This is the one that's going down to 0. Okay, halt lights on, and we're 12 seconds. Now, assuming my sums are correct, the inner loop does 65,536 jumps. So the total number for the program is 2 for the initialization plus 8 times the inner loop plus 1. And the extra 1 is for the second jump. That's about 524,000 instructions in 12 seconds. And that all works out to about 40,000 instructions a second, or 40 kips. Now this is only measuring that one particular instruction, but it's quite useful as I did it before with an earlier version of the machine, and I think I got about 50 kips, so I've obviously lost some with various enhancements. I might look at that later. Okay, let's look at some more examples. These are adapted from the computer course at Princeton University. Now notice there's no multiplication instruction in toy A, so how can we multiply two numbers together? And is there an efficient way? Well, we have an add instruction, so the simplest way is just to do repeated adds. If you multiply 5 by 3, that's the same as adding 5 to itself 3 times, 5 plus 5 plus 5. And 5 times 4 is 5 added to itself 4 times, and so on. Okay, let's try it. We'll use the keypad to prompt the operator for both numbers and display the result on the teletype screen. So first we need toy A, and now for the program. Apologies for any switches which magically change or extra numbers appearing on the screen without me doing anything. I had to edit out quite a few mistakes. Okay, reset, run. Keypad lights on, so we're waiting for a number on the keypad up to 4 digits. Let's try 5, do run, 3, run. Okay, there's the answer, 15. It seems to work. I'll try 9 times 4. There we go, 36. Okay, I can use bigger numbers, but note the keypad buttons represent hex digits and not decimal. So if I want to do 32 times 3, 32 is hex 20, so we want 2, 0. Next digit is 3, and there's the answer, hex 60 or decimal 96. Let's try a bigger number, 255 by 255, and that's FF times FF, so FF, FF, and there's the answer, 65,025. And this answer in hex FE01 is almost the largest number you can hold in 16 bits. So that's one limitation, but the other is more subtle. Now it looks like the answer was there in a flash, but what if you had to do thousands of multiplications? So let's put the whole thing in a loop so it does the same calculation repeatedly. We can then time it using the system timer. Now there's no nice decrement and jump instruction in toy A, so we'll just have to make the loop the hard way. There is a jump if 0, so I can preload a register and decrement it each time around the loop, and then use a jump if 0 to terminate the loop. I also need to postpone the result display on the teletype here and postpone it to the end of the loop as this adds a time overhead. Now in the more complex emulation, called Plex, the display has a status value, so the program can do other work while the screen is updating. But with the toy emulations, the program has no choice but to wait. Okay, so here's the same program but embedded in a loop. Right, this prompts for the two numbers, multiplies them 4,000 times and then halts. So here we go. 5 times 3 . Okay, 2 seconds. And the answer is still 15, which is good. Let's try 5 times 6. 5 times 6. Okay, a bit longer there, 4 seconds. How about 5 times 15, which is F. 5 times F. 5 F. Answer 75, good. And that's taken 8 seconds. Okay, we'll try 5 times 34, which is hex 22. 5, 2, 2. Okay, 18 seconds. Now, as you might expect, the time is increasing as the second number increases. Now, let's try the largest pair before the register overflows, which is 255 or FF times 255. This might take a while. FF, FF. Okay, just confirm the answer, 65025, and it took 1 minute 52 seconds. So is there a faster way? Well, this one is based on the old long multiplication method, which you may hopefully have covered at school. You treat each digit separately and then add the partial results together. And this should be less dependent then on the size of the numbers. Now, you may have spotted a catch-22. Treating each digit separately still means you have to multiply them. But we haven't got a multiply function. Well, the trick is that the digits in this case are binary, and it works out that the only multiply operations you need are powers of 2, which, if you remember from a previous video, is the same as shifting the binary number to the left. Shift 1 place to multiply by 2, shift 2 places to multiply by 4, and so on. And as luck would have it, we do have a shift instruction. So here we go. Okay, this is a single multiplication. Need to check it works first. That's its primary objective. 5 times 3, answer 15. Promising. And now the largest number, FF times FF. $65025. Okay, so the routine works. Let's adapt it for timing purposes. And I'll use a loop of 4,000 as before. Okay, this is 5 times 3, 5 times 3, 4,000 times. Okay, that's 18 seconds versus 2 for the repeated adds. So this method looks a lot worse at the moment. Let's try 5 times 6. 5, 6. That was 4 seconds on the previous one. Okay, 18 seconds. We'll try 5 times 15. 5 times F. Okay, well, it's a consistent time. Let's try the one that took 18 seconds before, which was 5 times 34. 5 and 34 is hex 22. Okay, well, let's go for broke and go for 255 times 255, which is FF times FF. Okay, well, this is a definite improvement over 1 minute 52. I won't bore you with any more. Suffice it to say that all numbers take roughly the same amount of time. So apart from a few exceptions with very small numbers, a bit of lateral thinking can make a big difference. Having said that, you may find faster algorithms use more memory, so there's more to consider. Right, that's it. I'll turn the machine off, and all that work is now lost because the main store in the toy emulations is volatile. So in the next video, I'll look at a very old school way of preserving your programs, paper tapes.